Hello and welcome to another video from our BeamTool tutorial video series. In this video, we want to take advantage of point respect function simulation and quality maps for phase array to further explore focusing option for our phase array inspection technique. In previous videos, we introduced the concept of point respect function simulation and show you how they can create quality maps that can guide us for selecting the optimum parameters for inspection technique. If you haven't had a chance to go through these videos, I encourage you to first go to those videos and get familiar with those concepts before coming to follow this video. For this case, we want to use an example of inspecting the axial piece with 20 millimeter thickness and the weld that has 30 degree bevel. In previous videos, we had a specific video on inspecting the axial pieces with phase array for phase array, and we discussed the corrections that can need to be made to compensate for curvature of that piece, those pieces. If you haven't had a chance to look through those videos, I again encourage you to go through that video first to get familiar with those type of corrections before you continue with this video. Okay, so for this example, what I want to show you I'm going to use for demonstration is this probe and wedge set. The probe is 5L32A11. It's a 32 element probe, 5 megahertz frequency and a pitch of 0.6. And the wedge that goes with it is SA11 wedge N55S, which creates a nominal 55 degree shear beam. So let's turn it on. So that's where, and it's going to be located 50 millimeter from the center of the weld on the basically on this direction. The common first approach or technique that I want to use or demonstrate would be a simple sectorial scan by center, a 16 element aperture at the center of the probe, as you can see here. And I want to create angles from 49 degree to 62 degree. So I can cover basically most of my bevel. And the idea is that this technique seems to be suitable because if you go to beam info section and highlight beams, seems like including all the corrections from the OD and ID of tracing these beams with Snell's law, at the end of the day, when we hit the bevel, we are hitting the bevel in the angles that are within 10 degree of the bevel and normal to the bevel angle. You see bevel angle as you can notice here. So this beam set and range of angles seems to be appropriate choice for this inspection with this offset. Okay, so now here I did not use any focusing. So the focusing is set to none in this case. Now, what I can do, I can go to my PA quality tab and try to simulate point respect function in the second skip to get the sensitivity. When I click on that, BeamTool tries to calculate point respect function and give me a nice preview of sensitivity. Okay, so now when I zoom in on the weld, you see a shadow of point respect function and a sensitivity distribution. So the sensitivity seems to be uniform more or less. If I move around, you see it's the value of sensitivity do not change much, and that's also clear from the palette. But what is really noticeable is how big this point respect function shadow is. To better understand that, I can go to vertical resolution, which ties into our height sizing, and notice that for a theoretical point that should be basically 0 in size, we are looking for something around 7 or even 8 millimeter or even 10 millimeter. So it means that we are really oversizing because we are not using a focus technique, and that's not really surprising. So the first idea that comes to mind is that, okay, let's take advantage of the focusing and now try to improve this sizing. So the first thing that may come to mind is that now, let me just get rid of this for a second. Okay, now first thing may come to mind is that let's just keep the same technique, but now instead use focus. So still 16 elements, same angles, same aperture size, same exit point. The only difference now can be that we can add a projection focus. And in this case, we chose to use a projection focus as around like 37 millimeter. And that basically put all these focus points along these beams here that is kind of very close to our location where our bevel is. So now in this case, what I can do now is to compare these quality maps for this focus technique with a previously unfocused technique. So, and we can go to, let's say, vertical resolution here. And on the previous one, also we switch to vertical resolution it was. And here you can choose to compare. And when you select compare, BeamTool asks you what group or technique you want to compare this to. And in this case, we want to compare with the unfocused aperture 16 of the same pro. So I click on this one. And now BeamTool starts to render these point respect function simulation and vertical resolution map for both technique. Okay, and it's going to plot them on the same color palette range. Perfect. So now I come here just to give a big view. The top with our unfocused technique, and the bottom one is the focus technique. But one thing that you notice, specifically if I zoom in, is that we don't see much of an improvement here. So although we use focusing, still you see that our range of vertical resolution and size of our point spread function is really similar. So it seems like focusing did not help us here at all. Now we want to know if this is surprising or not. We know that we don't have focusing capability at the region beyond the near field. So let's look at BeamTool again and go to these beam sets and try to go to the option to just give us a display near field. When I say display near field, what happens here is the near field length is right here, and it's far away from our region of interest. So we are far from our near field anyways. So then it would not be surprising that focusing would not have any effect. So you can see that we are trying to focus at the location that is already far from our near field. So it's not surprising that our focusing do not improve anything, because we are effectively actually not focusing. So now, how we can improve this? We can improve this by changing the parameters in our technique that can increase the length of our near field such that our near field get extended to our imaging domain close to our bevel. And the main thing that come in mind would be to increase our aperture size. So to show that, we can come first and get rid of this comparison, and also let's take out the previous simulations. Okay, now what we want to do, we want to keep the same angles, but now instead of using only 16 elements, that we used here, we want to use the full aperture. And you notice that, again, our beam exit points are the same, or the center of the aperture, because the 16 element aperture that we chose before was starting from element 9 on the center. And we didn't change our angle, so nothing has changed. And the same, we are using the same projection focus and at the same focus length of 37 millimeter. So now, realistically, the only thing that we changed in this new beam set that we show here with purple is basically our aperture. But based on our understanding and what is also mentioned in BeamTool help, the near field has a strong correlation with the size of aperture, with the factor of square. So if we increase our aperture, we really increase our near field. And that's what we can see here in BeamTool, that if now I show display near field, now you notice that all these green shadows passed and extend my near field all the way here. So now the location I chose to focus is within my near field. So now I can think that I can actually effectively focus here. And now focusing can actually have some effect. To see that effect, what we can do is come here and set vertical resolution that we want to compare against. And then here we try to again compare, say compare. And now we compare with our projection focused with 16 aperture that we saw before. We click on that. Beam tool goes and simulate point dispatch functions. And when it's done, I need to turn on the other one. And now, when I come here, I start to see a big noticeable difference. And to see that further, let's just focus on in this region. And to better see this, maybe I can also turn off don't show the beams. Show beams. Okay. Now, also you see from the palette is that on the bottom technique, which was focused with 32 element instead of 16, same beams, same exit point, just the fact that we use larger aperture, you see the vertical resolution improved like a lot by a factor of 2. Like here you can see that what we used size before around 7.5, now it's around 3.5 or 4. So now along the bevel, we have major improvement. So these basically show us that if we want to take advantage of focusing, we need to be sure that we are within our near field. And at that point is when we can take benefit from advantages of the focusing, which the main one would be here, that improve sizing because of the smaller focal area or focus, smaller focus size beam. Now, another thing that can come into mind is that maybe we can even further improve this, because another thing that can improve our focusing capability would be frequency. So, what another idea that can come into mind is that we increase our frequency, and that means that we move to another probe with the same frequency. So to see how that works, let's just remove these comparisons here and also remove these simulations at this point. And now let's look at I'll just want to turn off actually let's keep it on. So it's 32 element. This is the last technique that we looked at. It is a 32 element aperture, 49 to 62, and with projection focus. Now let's keep the same technique, but move to a probe and wedge that are higher frequency, meaning that now it's exact same probe in terms of number of elements and aperture, 0.6 and 32 element, but now we use a 7.5 megahertz frequency. So what this, and then we use exact same beams again with the 32 element aperture and from 49 to 62. Now, one thing you would notice, if now we turn on currently on the screen, because the previous beam is on, you kind of see the extent of the near field on when we had 32 element aperture with 5 megahertz probe. Now, if we turn on the display near field on this one, you see that it's going to be even further extended, because again, as you know, the frequency has a linear relationship with near field. As if we increase our frequency, our near field going to be increased. So now in this case, now what we want to do is to see if we increase our frequency help us in focusing in terms of increasing our vertical resolution. So what we can do here, come here and change the metric to vertical resolution for our new technique, and on our previous technique also we were on vertical resolution. So now what we can do is to hit compare, and now we will compare this with a 5 megahertz probe, 32 element aperture projection focused. And then BeamTool gonna go and do this simulation for us and give us a vertical resolution maps. So now again, the top one, the beams are not showing there. So if I come here, I can say show beams so that we have beams on both. But for simplicity to see the maps easier, let's turn off the beams on both cases and go to the maps. So the top one is when there are same beams, same aperture, but the top one is lower frequency, and bottom one is higher frequency. And again, you notice that our vertical resolution has been decreased further, or like increased further, and the size decreased further. So if I zoom in here, you notice now that in the bottom section, the vertical resolution is smaller. So we get closer to this actual size of point split function, which should be theoretically 0. So again, we improve by almost double by just increasing our frequency. So these tools and this concept is trying to show you how we can take advantage of these tools and playing with the parameters that we can more and more take advantage of focusing when we do the design phase array inspection techniques, because we know that there are many parameters involved in the focus quality, but having these tools would be very useful to give us a visual map to compare, to choose the optimum parameters so that we can take the most advantage from focusing with phase array. I hope that this video was useful to you. Thank you.